What's up guys, this is the Round Bottom Flask and welcome to the video lecture series on the electronic structure of atoms. This video is a part 2 of the 4-part series of lectures for this topic, and in this video we will be discussing the two latest models of an atom. Now I'm pretty sure you're very familiar with this experiment that when you allow a beam of light to pass through a prism, it splits to different colors, which is actually the colors that we see in a rainbow, in what we call as the continuum spectrum. So it is called a continuum spectrum because you do not see the boundary or the borderline between red from orange, between colors in general. So for example, if you don't actually see that there is a boundary between the color red and orange in the in the rainbow, but you see that the red slowly transitions to orange, up to yellow, and so on and so forth in the colors of the rainbow. Now let's say we have a hydrogen gas and then we allow it to pass we allow a high voltage to pass through that stream of hydrogen gas. Now when that high voltage passes through the stream of hydrogen gas, the atoms emit light, which is emit light at very specific colors or at very specific wavelengths. So if you see here, there is actually a separation. There is actually a separation between this line and this line here. It's not like what you see in the rainbow, that it transitions from this color to this color like a gradient, or for example, like the gradient feature when you color a shape in Microsoft Word or in Microsoft Office. So it doesn't work that way. In this case here, there are just specific lines or specific wavelengths wherein the hydrogen gas emits. So this is what we call as a line spectra or a line spectrum. So in 1885, a Swiss school teacher, Johann Balmer, showed that the wavelengths of the 4 lines of hydrogen fit in an intriguingly simple formula, which wherein it relates the wavelengths of those emitted light in the line spectrum to two whole number integers, which is called the Rydberg Equation today. So this is the Rydberg Equation, wherein we introduce a new constant here, which is the Rydberg constant, which is equals to 1.096776 times 10 to the 7th meters to negative per meter, and n1 and n2 is the whole number integers that described by Johann Balmer. Now, in 1913, this line spectrum was given an explanation by Niels Bohr. So, Niels Bohr, what he did in order to explain this line spectrum, he developed a more improved version of the solar system model of Rutherford's, the solar system model of an atom previously formulated by Ernest Rutherford, wherein he combined he combined the solar system model of Rutherford to the concepts established by Planck and Einstein in the photoelectric effect, which gives rise to this Bohr model of an atom. So in Bohr's model of the atom, its orbits of certain radii corresponds to a specific energy, and and it also and that energy is permitted to be the energy of the electron in a hydrogen atom or in a hydrogen-like atom. So when we say here a hydrogen-like atom, that means it is an atom with an electronic structure of a hydrogen atom. So remember that a hydrogen atom rather only contains one electron. So hydrogen-like atoms, therefore, are atoms that only has one electron. So an electron in an allowed energy state does not radiate energy and therefore does not spiral into the nucleus. So that means when it is in that specific orbit, that electron, unlike in Rutherford's model, does not implode into the nucleus, but rather it stays on that orbit with a specific integer here, as predicted by Johann Balmer. And lastly, an electron absorbs or emits energy when it transfers to one state or another. So if it jumps from a lower state to a higher state, obviously, since the higher state is higher in energy, it will need to absorb energy from the surroundings. But if it's from a higher energy state to a lower energy state, the electron, upon it when it goes down to the lower energy state, it will it will release energy. The amount of released energy, we will show that later on. Now, the energy for each orbital was obtained from the Rydberg equation, and also a manipulation of Planck's equation of the energy of a photon, which is equal to this one here. So again, we use here the Planck's constant, we use the Rydberg's equation, and the n here will be the energy level, or the whole number orbit wherein the electron currently resides. Now the energy difference, or the energy jump, when it jumps from one state to another, is equal to this formula here. This will be the final formula. Okay, so again, Bohr's model infuses both the concepts of both the solar system model of Rutherford and the and the quantized energy concept of Planck. Now, to further emphasize or further explain the quantized energy levels of the Bohr's atomic model, so French physicist Louis de Broglie, in his PhD thesis in 1924, proposed that electrons and, well, any form of particle or matter in general also behaves like a wave. So the wavelengths of that object that behaves like a wave, or what we call as the de Broglie wavelengths, is equal to this formula, wherein P will be the momentum and m will be the mass of the object or particle. Remember that the mass should be in SI unit, which is in kilograms, while the velocity of the object is in meters per second. And of course, we use the Planck's constant. So such objects that has wavelengths are called de Broglie matter, and the wavelengths of these de Broglie matter is called rather de Broglie wavelengths. Now, one property of de Broglie one rule that every de Broglie matter follows is that it cannot that we cannot exactly know the momentum or the velocity and the position of a de Broglie particle at the same time, and that principle is what we call as the Heisenberg's uncertainty principle. So to describe or rather to show how Heisenberg uncertainty principles, how Heisenberg's uncertainty principle works, we have this experiment here on the right. So we have our electron source here, which passes through the slits, okay? Which passes through the slits. Now, the slits, the electron here, since it is a beam of electrons, will pass through the laser beam. Now, the laser beam will will interact with the electrons such that the area when it hits the film, the light area here should be the area wherein the electrons and the laser beam interacts, okay? And the dark spots here is where there is no interaction between the electron or laser and the laser beam, because no electrons has passed there in the first place. Now, we know that it passes through here, but if we actually want to know that it passes through here, in order to confirm, that bright spot should be very fine, so it should be very defined here, so it does not fade away to gray and to dark like this one that we see in the picture, but rather it should just be one bright spot here that does not fade outward, okay? But since it fades outward, this just shows that we cannot accurately determine both the position and the momentum of the electron, because if we can accurately determine the position, this bright spot does not fade away, to black outward, okay? So mathematically, this is our Heisenberg's uncertainty principle. So therefore, the change in speed the change in position multiplied by the change in momentum should be greater than or equal to h over 4 pi, wherein the h again is our Planck's constant. So let's try applying this equation here to our problem. So the de Broglie wavelengths, so we have an electron with a mass of 9.11 times 10 to the 31st kilograms that travels at a speed of 5.97 times 10 to the 6 meters per second. So what will be its wavelength in nanometers? Also, let's say if the velocity has a 0.1% relative uncertainty, what will be the absolute uncertainty of the electron's position? So let's try solving first letter A. So for letter A, we just use the formula of de Broglie to get the de Broglie wavelengths, which is this one here. So we have the Planck's constant, we have the mass and the velocity of the electron, and this will be its wavelength. But since it is what is asked is in nanometers, we convert this to nanometers. So we know that so we have this one in meters here. We know that 1 meter is equal to 1 times 10 to the 9th nanometer. Okay, so we just multiply this one with 1 times 10 to the 9th, and you will get this answer here, which is 0.1218 nanometers. So let's try answering letter B. So we know that in our Heisenberg's uncertainty principle, this one here should not be less than the product of the change in position and of the uncertainty in position and the uncertainty in momentum should not be greater than, should not be less than h over 4 pi. So that means the lowest value that it could get should be h over 4 pi. Since in the Heisenberg's uncertainty principle, the relation is greater than or equal to h over 4 pi. So let's go back here. So now the electron's mass does not change, obviously, when it travels at a speed of 5.97 times 10 to the 6 meters per second. So this term here in the Heisenberg uncertainty principle, we can take out the m, or the mass, because it is a constant, so it will become this one here. So therefore, we can just get the uncertainty, this delta v here, which is the uncertainty of the velocity. So how do we get the uncertainty in velocity? We just get the 0.01% of our velocity here, since we have a 0.1% relative uncertainty. And that is equal to 597 meters per second. So we plug that into our Heisenberg's uncertainty principle, since what we're getting is the delta x here, which is the absolute uncertainty of the electron's position. So to get that, we treat this as an equation. So we transpose all the known values to the other side of the equation, plug in our values, and we have this answer here. So what does that mean? So that just means that the electron can be found within at least a 9.695 times 10 to the 8th meter radius. Okay, so imagine that the electron is roaming around a circle with a radius of at least, it can go bigger. It can go beyond that 9.69 times n to the times 10 to the negative 8th meter radius. So it can go beyond that. So it doesn't make any sense. So what does that mean? Well, that only shows that we cannot actually know where the electron is. We know its mass, we know how fast it goes, but because of the Heisenberg uncertainty principle, we cannot know where exactly the electron is. We can know where it probably is. So treat it like your Google Maps, okay? So let's say you have your search results here, and it shows you a radius of, let's say you search for nearby restaurants at a 2 kilometer radius. So it will show you an area wherein all of the restaurants nearby within the 2 kilometer radius, but it does not show you the exact distance from your position. So just like in marketplace, so if you search at this area, it will just show you in that area within the 2 kilometer radius. It does not give you the exact position kung asan yung restaurant na yon or yung place na iyon. It just shows na it's just within that area. Hindi mo alam kung asan talaga siya. I hope it makes sense to you. So let's try using that principle to a much larger object, say a baseball. Now we have a baseball with a mass of 146 grams, was thrown at a speed of 1.77 times 10 to the 6 meters per second. So what will be its wavelength in nanometers? The same problem. Okay, so let's try solving this one. Wait lang, may kodigo ako. To be fair, I already solved this beforehand. So don't judge me. So let's try solving first for letter A. Now for letter A, we just use the formula for getting the de Broglie wavelengths. So that means we treat the baseball as a de Broglie matter. So the Bruyn wavelength is equals to h, the Planck's constant, divided by the momentum, which is mass times velocity. So this is the mass in kilograms, and this is its speed in meters per second. So we have the Planck's constant here, which is 6.626 times 10 to the negative 34 joules per second. Then we have our mass here, but the mass is given in grams, so we convert this to kilograms. So we have 146 grams. We convert that to kilograms, so 1 kilogram is equal to 1,000 grams multiplied by the velocity, which is 1.77 times 10 to the negative to the 6 meters per second. So that is equal to 2.564 times 10 to the negative 39 meters. Converting it to nanometers, I'll get straight to the point. That is equal to 2.564 times 10 to the negative 30 nanometers. That is pretty small in relation to a baseball bat with a dimension of, let's say, with the diameter of, let's say, 4 inches or 3 inches. That's pretty small. Okay? So we have now the Bruyn wavelengths. I'll list it down here. So letter A, we have we have the Bruyn wavelengths, which is equals to 2.564 times 10 to the negative 30 nanometers. Then let's proceed to letter B, wherein we measure its relative uncertainty. So again, since the ball, when it's the baseball bat mid-flight does not change its mass, therefore, in our Heisenberg's uncertainty principle, what do they call this? So h over 4 pi, sorry. So that one, so this one here, since the ball does not change its mass mid-flight, so we can convert this to mass times velocity. Okay, in order to get this, we need to get the 0.01% of our velocity, which is 1.77 times 10 to the 6 meters per second, which is equals to 177 meters per second. Okay, so in order to know the uncertainty of the baseball's position, you transfer this term to the other side, so it would look like this. And we substitute our values, so that is equal to 6.626 times 10 to the negative 34 joule second. So we have 4 pi multiplied by the mass, which is 146 grams, convert this to kilograms, multiplied by the absolute uncertainty of its velocity, which is 177 rather meters per second. So that is equal to this one, guys, I did not solve beforehand, so well, but I'm pretty confident with my answer, hopefully, I guess. If there are corrections, please feel free to comment. Which is equal to 2.04 times 10 to the negative 36 meters. So that means you can find the baseball bat as a baseball. When it flies mid-air, it has a wavelength of this small, 2.564 times 10 to the 30 nanometers, and it can be found within at least a 2.04 times 10 to the 36 meter radius. Now that is really, really small. Oops, it was covered, sorry. So it was covered by my face, sorry. So x, so delta, so the change in x is equals to 2.04 times 10 to the negative 36 meters. I hope you can see. Yep, it's visible. Good. So let's delete that one, and we put our values here. So these values are really, really small in comparison to a baseball. Okay, so what does this mean? It means is that these laws that we have shown here, which is the laws of the quantum mechanics, can be applied to all objects, but it's really insignificant to those in the, if viewed in a naked eye. Okay. Now, the good thing about Bohr's the model of Bohr of an atom is that it can accurately explain the line spectra of hydrogen and hydrogen-like atoms. Now, the problem arises when we're trying to explain the line spectra of non-hydrogen-like atoms. So let's say we have atoms that here that has more than one electron. So let's say, for example, neon. Now neon, when we charge it, neon gas, when we charge it with a high voltage, its line spectra will look like this. Okay. Now Bohr can explain that for hydrogen because the hydrogen spectra is quite simple. Now what Bohr cannot explain in his model is these fine lines here. So how could that so that is one of the failures of the Bohr atom. So in 1926, the Austrian physicist Erwin Schrödinger proposed an equation that applies the de Broglie nature of matter. So here, so that what they call this? So that equation resulted to this famous relation here. Now this one here Now this the Greek letter psi here is what we call as the wave function, which describes the wave property of the electron. H hat here is what we call as the Hamiltonian operator. So the Hamiltonian operator is like a command that you would like to do that carries out a certain action towards a function. Okay? So think of it as if you had your calculus during your senior high school. So it's your d over dx in your differential calculus, and it's the integral sign in your integral calculus. Or to make it more simpler, operators are similar to your plus sign, your minus sign, your multiplication sign, and your division sign. So that is all operators, and it carries out a specific mathematical operation. That also what happens to a Hamiltonian operator. Now, Hamiltonian operator is actually an operator that allows you to compute the potential and kinetic energy of an electron with this given wave function, and that resulting answer upon operating a certain wave function with a Hamiltonian operator is what is the actual energy of the electron. And this famous equation here that revolutionized how we perceive electrons in atoms is what we call as the Schrodinger's equation. So this led to the development of the quantum mechanical model, or the electron cloud model of the atom. So currently this is the latest electronic model of an atom, and experiments in the decades followed by the establishment of the Schrodinger's equation further proves the electron cloud model as proposed by Erwin Schrödinger. So the premise of the quantum mechanical model is that it applies also the concepts of the electronic model of an atom by Bohr, wherein they occupy specific energy levels, wherein those energy levels have specific values, or as Planck say, quantized. And obviously there are de Broglie electrons are de Broglie behave like a de Broglie matter, so thus it has a wave-like character, which is described by its wave function psi. The exact location of the electron, obviously, since it is a de Broglie matter, obviously it follows the Heisenberg's uncertainty principle, wherein you cannot determine the exact location of the electron in the atom. However, what you can actually get is the area of probability that the electron is most likely found. And that can be mapped from its wave function. And that area of probability is what we call as an orbital. Now, to go a deeper look in, or a deeper explanation of the Schrodinger's model, or a deeper understanding of a Schrodinger's model, requires both higher chemistry and higher mathematics subjects, or courses rather, which is now beyond the scope of this video, or beyond the scope of general chemistry as a whole. So that's the end of my video for the atomic model. So I hope you learn a lot from this video. Don't forget to subscribe to this channel for more educational videos or chemistry tutorials. So this is the Round Bottom Flask signing off. See you guys